Dear students, welcome back to the lecture series on solid state. Today, we will have a discussion on a few problems based on Bragg's equation. In the previous class, we have seen how crystals are used as diffraction gratings for X-rays and also about Bragg's equation or Bragg's law, which is given by n lambda equals 2d sin theta, where lambda is the wavelength of the X-ray, d is the spacing between the adjacent lattice planes, theta is the incident angle, which is the angle between the incident ray and the scattered plane, and n is an integer where n equals 1, 2, 3, etc., which is also called the order of diffraction. Okay. Now, let us discuss a few problems based on this equation, that is n lambda equals 2d sin theta. So, using this equation, not only we can find the path difference, which is n lambda, but from this you can also find out the other parameters as well. For example, if we have to calculate the spacing between the planes, that is, you have to find out d, then this equation can be used as d equals n lambda by 2 sin theta. So, if in the question the values of the wavelength of the X-rays, the incident angle, the order of diffraction is given, then from that equation you can find out the value of d. Similarly, if we have to find out the incident angle, if other parameters are known, so using the same equation you can find out the value of sin theta. So, sin theta is equal to n lambda by 2d. So, from that you can find out theta. So, theta will be sine inverse of that value. So, in a similar way, you can find out one parameter if the values of other parameters are also given. So, let us discuss a few problems. The first question, first order diffraction was observed for X-rays of wavelength 0.0576 nanometers at an angle of 6 degree 54 minutes for a single crystal of a certain solid. Calculate the distance apart of consecutive planes. So, in this question, you have to calculate the distance between the successive planes. So, first let us write the Bragg's equation. So, we have the basic equation n lambda equals 2d sin theta. Okay. It is given that first order diffraction was observed. First order diffraction means the value of n equal to 1. The wavelength of the X-rays are given, that is the value of lambda, lambda is equal to 0.0576 nanometers. The angle theta is given, theta is equal to 6 degree 54 minutes. Okay. So, all these values are given and now we have to find out the distance. So, from this equation we can find d, that is d is equal to n lambda by 2 sin theta. So, that is equal to n is 1. So, 1 into the wavelength lambda is 0.0576 nanometers divided by 2 into sine 6 degree 54 minutes. So, theta is given as 6 degree 54 minutes. So, that minutes has also to be converted into degree. So, 6 degree 54 minutes is 6.9 0.9 degree. So, you can convert it using 6 degree 54 minutes is equal to 6 degree plus 54, and you have to divide by 60, 54 by 60. So, that will be approximately equal to 6.9 degree. Okay. So, instead of sine 6 degree 54 minutes, now you can write 6.9 degree. The value of sine 6.9 degree is 0.1200. Okay. Then you can substitute this. So, that is equal to 0.0576 nanometers divided by 2 into 0.1200. So, this will be equal to 0.2397 nanometers. So, using Bragg's equation, we can also calculate the distance between the lattice planes. Now, we will move on to the second question. The diffraction of a crystal with X-rays of wavelength 2.9 into 10 to the power of minus 10 meters gives a first order diffraction at 27 degree 8 minutes. What is the distance between the lattice planes? So, again you have to find out the distance between the lattice planes. So, let us start with the Bragg's equation. We will solve it step by step. Okay. So, n lambda is equal to 2d sin theta. Now, let us write the known parameters. It is given the diffraction of crystal with X-rays of wavelength. So, lambda is given, lambda is equal to 2.9 into 10 raised to minus 10 meters. 2.9 into 10 raised to minus 10 meters. It is given that it is a first order diffraction. So, if it is a first order diffraction, the value of n is equal to 1. The angle is given, that is theta is given, theta is equal to 27 degree 8 minutes. Now, we have to find out the distance between the lattice planes. So, from this equation, from Bragg's equation, we can calculate d as d equals n lambda by 2 sin theta. So, again 27 degree 8 minutes is approximately equal to 27.133 degree. Okay. So, when we substitute this, we get 1 into the wavelength lambda is 2.9 into 10 raised to minus 10 meter divided by 2 into sine 27.133 degree. And sine 27.133 degree is 0.45606. So, we can substitute that value. So, we get d equals 2.9 into 10 to the power of minus 10 meter divided by 2 into 0.45606. So, this will be equal to 3.18 into 10 to the power of minus 10 meters. Now, we will move on to the third question. At what angle would the first order diffraction be observed in X-ray diffraction of a set of crystal planes for which d is 2.04 into 10 to the power of minus 10 meters. If the X-rays used have a wavelength of 1.54 into 10 to the power of minus 10 meters. At what angle would the second order diffraction from the same set of planes be observed? So, there are two questions here. First, you have to find out the angle at which the first order diffraction will be observed. You have provided with the value of d and also the wavelength. And the second question is, if it is for a second order diffraction, what will be the angle theta? Okay. So, now let us solve this step by step. Again, writing the Bragg's equation, we have n lambda equals 2d sin theta. So, let us solve the first part. The first part, we have first order diffraction. So, we have n is equal to 1. The d value is given, that is the spacing is given, d is equal to 2.04 into 10 to the power of minus 10 meter. The wavelength is given, that is lambda is given, lambda is equal to 1.54 into 10 to the power of minus 10 meter. And we have to find out the angle at which this diffraction occurs. So, from this equation, that is n lambda equals 2d sin theta, we can find out sin theta. So, sin theta will be equal to n lambda by 2d. We have n is equal to 1. So, sin theta will be equal to 1 into the wavelength lambda. So, it is 1.54 into 10 to the power of minus 10 meter divided by 2d. So, 2 into the distance 2.04 into 10 to the power of minus 10 meter. So, we will get the value of sin theta as 0.3775. So, if sin theta is equal to 0.3775, from this we can find the value of theta. Theta is equal to sin inverse 0.3775, and that will be equal to 22.17 degree. Okay. So, we have solved the first part. We have find out the angle at which first order diffraction will occur. And now we will move on to the second part. So, second part, it is given at what angle would the second order diffraction from the same set of planes can be observed. So, let us find out. Again, we have the equation sin theta is equal to n lambda by 2d. Here, on the second part, we have to find out the second order diffraction. So, what will be the value of n? The value of n will be equal to 2. So, sin theta will be equal to 2 into the wavelength. The wavelength is lambda, it is 1.54 into 10 to the power of minus 10 meters divided by 2 into d is the spacing, and spacing is 2.04 into 10 to the power of minus 10 meters. So, you will get the value of sin theta as sin theta is equal to 0.7549. And if sin theta is 0.7549, then we will have theta is equal to sin inverse 0.7549, and that will be equal to 49 degrees. Okay. So, we have solved the first part as well as the second part. Now, we will move on to the fourth question. The first order reflections from the 100, 110 and 111 planes of a crystalline substance was observed at the glancing angles 5.38 degree, 7.61 degree and 9.38 degree respectively. So, calculate D100 is to D110 is to D111. That is, you have to calculate the ratio of the interplanar distances from various planes. And also, you have to find out to which cubic lattice does the substance belong. Okay. So, here you have to calculate the spacing between the planes D use with 3 different planes. You have the 100, 110 and 111 planes, and you also have to find out to which cubic lattice does the substance belong. Okay. So, let us write the fundamental equation, that is the Bragg's equation. We have n lambda equals 2d sin theta. So, in this equation, if we take d, so d is equal to n lambda by 2 sin theta. Okay. So, suppose the other parameters are constant. For example, if n is a constant, the order of diffraction is a constant and the wavelength we use are also constant, then we can write d is proportional to 1 by sin theta. Okay. Now, consider the planes given in the question. Okay. So, we have a 100 plane. So, let the diffraction from the 100 plane occur at the glancing angle theta 1 is equal to 5.38 degree. So, next is the 110 plane. So, the 110 plane, let the angle be theta 2 is equal to, the next angle is 7.61 degree. And the next plane is 111 plane. And let us denote the angle as theta 3, and theta 3 is equal to 9.38 degree. 9.38 degree. Okay. So, we have the angle of incidence theta 1 from 100 plane as 5.38 degree, theta 2 from 110 plane as 7.61 degree and theta 3 from 111 plane as 9.38 degree. Okay. So, we can write the ratio. You have to calculate the ratio D100 is to D110 is to D111. So, that will be equal to, since D is proportional to 1 by sin theta, you can write here 1 by sin theta 1 is to 1 by sin theta 2 is to 1 by sin theta 3. Okay. So, theta 1 is sin 5.38 degree. So, that is equal to 0.0924 and theta 2 is 7.61 degree and sin 7.61 degree is 0.1323. Theta 3 is 9.38 degree. So, sin 9.38 degree is 0.1633. So, you can substitute the values here. We get 1 by 0.0924 is to 1 by 0.1323 is to 1 by 0.1633, and that will be approximately equal to 1 is to 0.6986 is to 0.566. So, we have solved the first part, we have calculated the ratio of the interplanar spacings. Now, the last part, to which cubic lattice does the substance belong? So, this ratio, that is 1 is to 0.69 is to 0.56 corresponds to the theoretically predicted for a simple cubic lattice, that is it is 1 is to 0.707 is to 0.573. Okay. So, it is almost close. We have 1 is to 0.69 is to 0.56 and the theoretically predicted value for a simple cubic lattice is 1 is to 0.707 is to 0.573. So, that means this substance belongs to a simple cubic lattice. So, using Bragg's equation, we can also identify to which cubic lattice does the substance belong. Now, we will move on to the next question. The first order Bragg's reflection from the 1, 0, 0 plane of a cubic crystal with d spacing d100 is equal to 4.5 angstrom and it occurs at a glancing angle of 19 degree. Calculate the wavelength of the X-rays used. So, in this question, we have to calculate the wavelength lambda of the X-rays. So, let us write the equation. We have n lambda equals 2d sin theta. N lambda equals 2d sin theta. First, let us write the known parameters. It is a first order diffraction. So, we have n is equal to 1. The diffraction is occurring from a 1, 0, 0 plane and the spacing of d100 is equal to 4.5 angstrom. Either you can represent it in angstrom or if it is in meters, you can represent as 4.5 into 10 to the power of minus 10 meters. Now, the angle is given, it occurs at a glancing angle of theta is equal to 19 degree. So, theta is equal to 19 degree. Now, we have to calculate the wavelength of the X-rays. So, from this equation, that is n lambda is equal to 2d sin theta. So, what will be lambda? Lambda is equal to 2d sin theta divided by n. So, that is equal to 2 into the spacing is 4.5 angstrom. So, 4.5 angstrom into sin theta. Theta is 19 degree. So, it is sin 19 degree divided by n. N is a first order diffraction. So, the value of n is 1. Now, sin 19 degree is equal to 0.3256. So, you can substitute the value of sin 19 degree. So, that is equal to 2 into 4.5 angstrom into sin 19 degree. So, that is 0.3256 divided by 1. So, when we substitute this, we will get the value in the angstrom itself, that is 2.9304 angstrom. If it is in meters, you can represent it as 2.9304 into 10 to the power of minus 10 meters. Okay. So, using the same Bragg's equation, you can also calculate the wavelength of the X-rays used. Now, we will move on to the next question. The first order reflection of a beam of X-rays of wavelength 1.54 angstrom from the 100 plane of NaCl occurs at a glancing angle of 15.9 degree. Calculate the edge length of the unit cell. So, this is a slightly different question. you have to find out the edge length of the unit cell, that is edge length is A, and you have to find out that using Bragg's equation. So, let us see how to solve this. First we can write the Bragg's equation, that is we have n lambda equals 2d sin theta. It is given that the diffraction is occurring from the 1, 0, 0 plane of NaCl, okay, and NaCl, that is sodium chloride, has a FCC lattice, that is it has a face centered cubic lattice, and the edge length of its unit cell A is equal to 2 into d, where d is the spacing between the planes. So, A equals 2d, d100. It is actually the same as d200. Okay. So, NaCl has an FCC lattice and the edge length of its unit cell is A equals 2d. So, if we find out 2d using Bragg's equation, that means you can find out the edge length A. Okay. Now, let us write the known parameters. It is given, it is a first order reflection. So, we have n is equal to 1. The X-ray wavelength is given, that is lambda is given, lambda is equal to 1.54 angstrom. If it is in meters, that will be 1.54 into 10 to the power of minus 10 meters. Now, the glancing angle or the angle of incidence is given as theta is equal to 15.9 degree. So, it is 15.9 degree. Now, what you have to find out? You have to find out the spacing between the planes. So, we have n lambda is equal to 2d sin theta, or we have 2d is equal to n lambda by sin theta. So, when we substitute these values, we get 2d is equal to, n is a first order diffraction, so the value of n is 1 into, the wavelength is given, it is 1.54 angstrom divided by sin theta. So, sin theta is sin theta is 15.19 degree. So, let us find out what is sin 15.9 degree. It is 0.2740. So, let us substitute the value of sin 15.1 degree. So, we have 2d is equal to 1.54 angstrom divided by 0.2740. So, that will be equal to 5.619 angstrom. Okay. So, we got 2d is equal to 5.619 angstrom. So, and what you have to find out? You have to find out the edge length of the unit cell. So, as we mentioned earlier, for an FCC lattice, the edge length A is equal to 2d. Therefore, the edge length A will be equal to 2d, that is 5.619 angstrom. Okay. So, in this way, using Bragg's equation, you can find out the spacing between the lattice planes. You can find out the angle, scattering angle or diffraction angle theta. You can find out the wavelength of the X-rays used, and also from the d value we can calculate the edge length of the unit cell. In the next class, we will continue our discussion on a few more problems based on Bragg's equation. Thank you.